So we'll go over chapter 9. We'll start the review. So chapter 9 is on acids and bases and buffers. And so there are different theories that have been put out there for what is an acid and what is a base. There was the Arrhenius theory and then the Bronsted-Lowry theory. And according to the Bronsted-Lowry theory, an acid is a proton donor and a base is a proton acceptor. And so when you have an acid and it will donate its proton, then it becomes the conjugate base, right? So the first exercise here is to write the chemical formula of the conjugate base of water and the ammonium ion. So that means you need to consider those as your acids, and you need to find the formula of what they become when they have donated their proton. So let me maybe write something here. So think about it. Do you know what a proton is? So acids are proton, and a proton is an H plus donors. So H plus, H is hydrogen, and it's the cation H plus. Because hydrogen, first element in the periodic table, atomic number 1, has 1 proton and 1 electron, and some hydrogen atoms, some isotopes, they have a neutron or 2 neutrons or 3. But the main hydrogen atom has no neutrons, and so it's just 1 proton and 1 electron. And when that hydrogen atom loses its electron and becomes H plus, then it's only a proton. That's why it's called a proton donor. A proton donor is an H plus donor, right? So H2O here is an acid, and when it becomes the conjugate base, it's because it has lost the H plus. So what you want to do to find the conjugate base, you want to remove an H plus from the formula of H2O. So remove an H plus from H2O. So if you want, you can give me the formula you come up with in the chat. I'm just helping for those who don't know yet. So when you remove an H plus from H2O, you're left with only 1 hydrogen, right? Okay, H2O is a bit particular because normally you would keep the formula, in the order that the elements come in. But here we will write OH instead of HO, which is the same. So we have lost 1 hydrogen, so there is only 1 hydrogen. So the subscript 2 here disappears because it's a subscript of 1 for hydrogen now. And when hydrogen plus leaves H2O, it leaves without any electrons. So it leaves behind the electrons. And so that will be extra electrons for OH. And so that means OH now will have a charge, a -1 charge. Does it make sense? So the conjugate base of water, if water is an acid, is OH minus. And the difference between H2O and OH minus is an H plus. So H2O as the acid, because it's the acid here, it has the H plus in its formula. And the conjugate base, OH minus, doesn't have the H plus in its formula anymore. So that's the difference between the two. And that's what water becomes when it donates a proton and acts as an acid. So the way to verify that is that, you know, verify by adding H plus to OH minus. If you add H plus to OH minus, you see that you will retrieve the H2O formula, right? I make the negative signs larger because otherwise they're really tiny, right? If you put those together, you can see that then you will have two hydrogens, and then the positive charge will cancel the negative charge, and you will get back H2O. So that's how you verify the symbol for your conjugate base. So let me put this in red so we know this is the answer. Does it make sense? Okay. So let's do the same with NH4+. So let me tell me what would you think is the conjugate base symbol for NH4+. So do the same, remove an H plus from NH4+ to get the conjugate base, because the conjugate base is obtained when the acid donates its proton. Yes. So again, we could say that we need to remove an H plus from NH3, NH4+, sorry, NH4+. So remove an H plus from NH4+, your acid, and I see you get it. So when you remove an H, the subscript 4 decreased by 1 and it's NH3. And when the H plus leaves with its positive charge, then NH3 becomes neutral, right? It removes the H plus. So, and you can verify, again, verify by adding H plus to NH3. So if you add H plus to NH3, you can see that then you will get 4 hydrogens. So the 3 becomes a 4, and then the H plus comes with a positive charge that is not cancelled, and so that is becoming an H4 plus. So that would be the conjugate base of, this is very big. Oh. Okay. Let me just change that, it's a bit too big. Okay, so that's our conjugate base. Let's do the reverse process now, because we are looking for the conjugate acid. So these are your bases, H2O and Cn-1. They are your bases, and you want to find what they become when they are so a base, let's remind you that a base are proton, so H plus again, acceptors. So they are accepting the protons. Proton acceptor. So that means these are your bases, and they will accept a proton and become the conjugate acid. So that means you want to add an H plus to them. So what is the conjugate acid of H2O? Yes. So from 2 H's you get 3 H's. So the subscripts increase by 1, so from 2 to 3, because you get one more hydrogen. And then H2O was neutral, and the hydrogen, the proton here comes with a positive charge. And so it cannot be cancelled. So that's going to be your conjugate acid of, oh, this is right, conjugate acid of water, right? When water acts as a base. So I need to say something that water is what we call an amphoteric substance. Let me write this. Water is amphoteric, which means it can act as an acid or a base. It can do both. Amphoteric is the term to say that. Can act as an acid or a base, depending what you put it with. So when it acts as a base, it's a proton acceptor, accept protons and become H3O+. Okay, so Cn-1 is the cyanide ion. So let's add H+ to it, make it accept a proton. As a base, it's accepting a proton and becoming. So tell me in the chat, what do you think is the conjugate acid of HCN? So typically when you are you have an acid, H should be written as first in the formula. Yeah, it's not always true, but you know, there are some exceptions, and water and ammonium here were exceptions where, you know, it's not the case, but most of other acids are like that. So you would write the H as first in the formula. Then you have carbon and nitrogen. And the H comes with a positive charge, but the cyanide ion had a negative charge. And so a plus, a minus, they cancel out. And so HCN is neutral. Okay, and that's the hydrocyanic acid. Okay, so this is the conjugate acid. You know, HCN is the conjugate acid of Cn-1. Oh, yeah, let me put this in blue because this is a... Okay. So you can see then that we can call these, you know, for example, water and OH minus. We are calling that a conjugate acid-base pair. And NH4 plus and NH3 together are a conjugate acid-base pair. H3O plus and H2O. So we tend to say the acid first. So H3O plus and H2O are another acid-base conjugate pair. And then HCN and Cn-1 are a conjugate acid-base pair. Right? Because they form a pair, because the only difference between the formula of the acid and the base is just an H plus. Okay, so I took this, let's look at problem 3. I took this image from your book, and it doesn't look great because we see what's in the back of the page. I hope you see the drawings clearly enough. So these diagrams represent 3 acids, and the generic formula for an acid is HA, right? A for acid, the H because an acid has a nitrogen, you know, to donate. So that's why we write them like that. And so here, if you look at the model of HA, it's a blue ball with a white ball. The white is the hydrogen atom. It's a small atom. And then the blue is representing the A. And A can be anything, like above we saw, Cn would be the A, right? Or, you know, so that's an easy example. So HA, when it donates its proton, becomes A minus, right? When you remove the H plus from HA, it becomes A minus because the H plus leaves with a positive charge, which means it leaves behind the electrons and they show up as a negative charge on the A, symbol A, right? And the third model here with the red ball surrounded by 3 white balls that represents the hydronium ion. That's the name of H3O plus. That's the hydronium ion, H3O plus. So in diagram A, we can see a lot of HA, you know, the blue and white balls bonded together. And then we see 2 A minus and 2 H plus. In the diagram B, we see a lot more H3O plus. So 3 H3O plus, 3 A minus, and then the rest are HA. And then in diagram C, you see only 1 H3O plus, only 1 A minus, and then the rest are HA. So which representation shows the strongest acid and which representation shows the weakest acid? So maybe before we answer that, let me write that HA, when it dissociates, let me do that in, so HA, oops, when it dissociates, so let's put a double arrow. We don't know if it's a single or double arrow, but here HA dissociates into A minus, that's the conjugate base. Let me not do that. So A minus, it's the conjugate base of the acid HA. And yeah, I guess here on top I should have added H2O, right? When you place it in H2O. Then the H plus. So the reason why the H plus is not just written as an H plus here, it's because when you have H plus, the proton in water, it's never floating around as an H plus. It's actually binding to a molecule of water. And so the H plus is actually found as an H3 O plus. Oops, sorry. No. Okay. So what happens is that the H plus binds, takes one of the lone pair on the oxygen of the molecule of water. It binds to one of these lone pair and makes a third single bond. And so oxygen is surrounded by 3 hydrogens, single bonded to 3 hydrogens. And then there is still one lone pair. And then it carries a positive charge because H plus comes with a positive charge. I really don't like the way I show this. Actually, I should put the H2 here. It would be better. Oh, no. Oh, yeah. It looks awful now. Hold on, I'll go back. Okay. So this, let's make it H2O as a reactant, and then it will make more sense. Okay, so when you add the acid into water, the acid donates a proton to water. The water then becomes the H3O plus when it binds to the proton, H plus, and then the acid becomes the A minus, the conjugate base. Yeah, I guess that's how we should see it, right? It's a transfer of proton from the acid to the base, and then water here acts as a base. So the proton went from the acid to the base. The acid donated the proton, the base accepted the proton, and that's what they become. So here, this is the, so we can write that under here. So HA is our, oops, HA is our acid. The water is the base. And we are having, so A minus is the, we call it the conjugate base of the acid, right? A minus is the conjugate base of the acid. And then H3O plus is the conjugate acid of the base. And the base here was water, right? So let's put all of this in blue. So, okay. So the H3O plus is the conjugate acid of the base, and the base was water. So that's how you want to see that. So we have this happening in both three cases, in both in three diagrams, but to a certain degree, right? In A, only two HA have dissociated into A minus and H3O plus. In B, three of them have dissociated into A minus and H3O plus, and in the case of C, diagram C, we have only one HA that has dissociated into A minus and H3O plus. And so you have to decide from that which one is the strongest acid. And so can somebody has an idea, or which one is the stronger acid? Yes. So the stronger acid is the one that would, you know, completely dissociate. Here we don't have an example of completely dissociate. This is not completely dissociated even in diagram B. It's only partially dissociated. But the strongest of the three is B because it's more dissociated than the others. So the stronger the acid, the more dissociated. The more it dissociates. Oh, okay, the more the acid dissociates into its conjugate base. The stronger the acid, the more the acid dissociates into its conjugate base. So diagram B represents the strongest acid here. It's not a strong acid because it's not completely dissociated, because a strong acid would be completely dissociated. You would not see any more HA, you know, undissociated. They would be all dissociated into A minus and H3O plus. If it was what we call a strong acid, you know, the arrow in the equation here, the arrow would be just a straight arrow to the right, right? It completely dissociates into A minus and H3O plus, and that's a strong acid. That's not what this is representing. So we only say here is the strongest of those three. And so the weakest, which one is the weakest then? Diagram A, B, or C? Tell me the weakest. The acid. Yes. See. So diagram C here represents the weakest acid, because it's the one that dissociates the least. And so I don't know if this recalls something about electrolytes. Maybe it gives you a vague memory of electrolytes, strong electrolytes and weak electrolytes. And it's all about, it's the same principle. A strong electrolyte is an electrolyte that, completely dissociates into ions in water. And so strong acid are strong electrolytes. They will completely dissociate into ions, A minus and H3O plus, and they will strongly conduct electricity. And a weak acid is a weak electrolyte. It only partially dissociates, so that's when you see the double arrow. It only partially dissociates into ions, and so the small proportion of ions it has can carry a little bit of electricity, so it weakly conducts electricity. So that's the same, that comes from the same definition, right? The strength comes from that. So the weakest the acid, the less the acid dissociates into its conjugate base. Okay. There is another way to check the strength of acids and bases, and it's by calculating the equilibrium constant. And that's why I wanted to have chapter 6 done before we do chapter 9, because that can be revisited here, and it's useful to check the strength of an acid. So let's do problem 4. Predict the products and identify the acid, the base, the conjugate acid, the conjugate base in the following acid-base reaction. And so here you have the reactant. You have HC2H3O2. It's an aqueous solution in water, H2O, and water, because it's the solvent here, it's liquid. We never put aqueous for water. Water would always be liquid or a gas or solid, but not aqueous. So which one do you think will be acting as an acid here? Because we know water could be an acid or a base. So water will behave depending on what it is put with. And here HC2H3O2. What do you think this is? Is it an acid or a base? So tell me in the chat. Do you think it's an acid or a base, given the formula? Yes. So it's acetic acid, and acetic acid is written in many ways. It could be, so if you look at, let's look at the reference page here. So if you are in the, let me just show you, this is the reference packet, right, for Chem 121. Page 1, 2, 3, 4, 5 is all about chapter 9 and acids and bases. So you want to have that page out if you have your reference packet. And here the table on top of page 5 here lists acids and their conjugate base. And it shows how on the left side, acids are listed in increasing acid strength going from bottom to top. So the strong acids are on top, weak acids are on the bottom. And in there, you can see acetic acid. So from the bottom, you move from water, hydrocyanic acid, ammonium. We have seen those two. Carbonic acid, and then acetic acid is there. And you see the formula doesn't look the same, but it's actually the same. If you pay attention, the H that is completely to the right now is in the front. And then the two C's are together, then H3, and then the two oxygen. So this is acetic acid. Same formula, but written differently. And the reason why it's written like this here, it's showing you how, it's bonded together. This CH3COOH gives you a better idea of the Lewis structure. So let's go back to the review. So we have acetic acid here, so that's going to be our acid. So let's write under that it's the acid, and then water will be the base. Because if you have an acid, then the other reactant is your base, right? They cannot be both acids. When you have an acid-base reaction, I mean. So the acetic acid is your acid. So the acid donates a proton and the base accepts the proton. So let's find out the formula of HC2H3O2 when it loses a proton and donates the proton. And the proton that goes away is the first H in the formula, and that's why acids are written like that. It's to show which H, which hydrogen goes away. So that means here you will be left with, and let me do this so, okay, so we keep C2H3O2 and it's still aqueous. We lost the H that was first in the formula, and it's an H plus that went. So we have removed the H. Now let's remove the positive charge. When you remove H plus, so it leaves without the electrons. So that means here the bond you had now becomes a lone pair, and it's bringing a negative charge, right? So this will have to have an, oh, no. Oh. Let's see. It's hard to put down a negative charge. Okay, so negative here, and put this whole thing here. Okay. Okay, so this is the acetate ion. So acetic acid becomes the acetate ion when it donates its proton. And so water now will accept the proton as a base. It will accept the proton, and so H2O plus a proton becomes H. So we have now 3 hydrogens, oxygen, and the hydrogen came with a positive charge. And this is aqueous, right? So that's how you find the product of this acid-base reaction. No, not that. So here I will put just a single arrow, but it should be a double arrow. So which one is the conjugate acid and which one is the conjugate base? Because we need to identify that. So C2H3O2, is it the conjugate acid or conjugate base? So tell me, conjugate acid or conjugate base? Yes, it's the conjugate base because it came from the acid, right? The conjugate base must be the one that came from the acid. And then H3O plus is the conjugate acid, right? Of course, because if the one is the base, the other has to be the acid. It's the conjugate acid because it came from the base, right? The water was the base. Water, when it accepts a proton, becomes H3O plus. So H3O plus is its conjugate acid. Okay, so that's how we would identify the acid, the base, the conjugate acid, the conjugate base. Okay, so that answers the first question. Do you have questions on that, or? So, and you see that it's balanced. There's no mention of that because it's balanced. The H plus was just transferred from one reactant to the other, and there's no need to change the balancing here. Okay, so using this chemical equation now, write the equilibrium constant. And this is chapter 6 material, right? The equilibrium constant. And let's look at the formula of the equilibrium constant. If you go back to your reference paper, back to page 1, the top left corner has the material for chapter 6. And here, I'll put it in the middle. Equilibrium constant, Kc, is the concentration of product over the concentration of reactant. And, with more details here, the coefficients become exponent for each concentration. So let's remember this formula and apply it here. So Kc equals, and the C is a subscript. So Kc is, concentration of product over concentration of reactants. So here we have on the product side is the right side. So on the right side we have H3O plus, so H H3O plus times C2H3O2. Let's see if I can copy that. Okay, so that's the two products multiplied together. They have no exponent because they have coefficients of 1 in front of them, so they stay like this. And then on the denominator, we have the concentrations of the reactant. And so here, you have to be careful. Water is a liquid, right? Remember, and I know it's easy to forget, remember liquids and solids are not included in the equilibrium constant. So it's going to be only, and I will use this I had earlier. So H, C2H3O2, and that's our acid. No, okay. Oh boy. Oh no. Trouble with those formatting. Okay, sorry. The acid HC2H3O2, okay? Okay. So that's the expression of the equilibrium constant. And here, because the reaction is an acid dissociation here, because it's in water, we place the acetic acid in water, so we can see this equation as the acid dissociation of acetic acid. So then it's, yeah, by the way, it's not Kc, but Ka. It's a acid dissociation constant, so it's called Ka in this case, right? So Ka is this expression. So now we have this expression and we have values that we can plug in we have values of the concentrations. Remember that when you have brackets here, it means concentration in molarity, actually. So let's take this and copy it here and then complete it with the values. Now we can plug in the values. So what is the Ka value? If the equilibrium concentrations are for the acid 2 molar, H3O plus is 0.006 molar and the concentration of the conjugate base is 0.006 as well. So let's place those numbers. So 0.006 times 0.006. So, right, the H3O plus is that. The conjugate base, we know it's the acetate, right? It's the one on top here. And then the acid is the acetic acid on the bottom. So the 2 molar will go on the bottom. And so in your calculator, you do this. So 0.06 squared divided by 2. And it's, let's write it in scientific notation. 1.8 times 10 and 10 to the -5. Is it what you have also? So that's the value of the Ka. The Ka has no units. Remember the equilibrium constants, they have no units because you see here it's molar squared above divided by molar, so it would be molar, but sometimes given the expression it can be any kind of unit, so because of that it's unitless. So 1.810 to the -5 is the acid dissociation constant here. So you know that, from chapter 6, given a Ka value or a, equilibrium constant value, we can decide if we have more product or reactant, right? And this comes from the formula here, because the Ka is concentration of product over concentration of reactant. So here is Ka very, very large or very, very small? So tell me, do we have a very large value or very small? Very small, right? It's much smaller than 1. Ka is much smaller than 1 because it's 110 to the -5. So it's 1.8 divided 5 times by 10. So it's a small number. So it's very small compared to 1, which means if you move the reactant to the right side of the equality here, you have a concentration. So I could continue here, which means concentration of reactants is, and maybe I'll start from concentration of product, is very, very small compared to concentration of reactant, right? Because from the Ka expression, we know that means we have a very small numerator and a very large denominator. So that means the which means reactants are favored. Oops, yeah, that's not good. Let's remove that from here. Okay, so reactants are favored. We don't see the equilibrium. Would be nice to have it. So reactants are favored here. That means the acetic acid and the water are favored and in larger concentration. And this is confirmed by the concentrations. If you look here, the acid has a concentration of 2 molar. And the conjugate base only 0.06 molar. So it shows you how, yes, we have much more reactant than product. So is this a strong acid or a weak acid, given that you can decide which one is, you know, if it's a strong acid or a weak acid by knowing that the equilibrium is shifting to the left, you know, favoring the left, and you have more acid and water than you have the products. So does it mean you have a strong acid or a weak acid? If you think about, you know, what makes a strong acid? Yeah. It's a weak acid, very weak acid, because it's dissociating very, you know, in a very small proportion, right? It's mostly the acetic acid, the neutral molecule, and then only a small proportion of ions. So it's weakly conducting the electricity. It's weakly dissociating. You know, only a small fraction is dissociating. So that's, you know, definitely a weak acid. It is a weak acid. Okay, so now, what is the pH of the solution? So, if you've been far enough, yeah, let me. So, if you go back to the reference packet, page 5 of it, below the table where it lists the acids and conjugate base, you have these formulas for the pH, the ion product constant of water. But here, first, let's look at the pH. So pH is a way to give the acidity or basicity of a solution without, you know, having to rely on the concentration of hydronium ion, because concentrations are, you know, small numbers. You know, they are always typically in scientific notation with negative exponent, right? The H3O plus concentrations, you should expect that. Sometimes if it's large, it's, you know, 2 molar, 1 molar, but most of them will be times 10 to the negative exponents and be small values, and it's hard to judge the strengths based on that. So then there was this pH scale created, which is a logarithmic scale that allows you to see the acidity more, you know, readily. And so to calculate the pH, you do the negative log of the concentration of the hydronium ion. And then the pH goes from 0 to 14. So it's much easier to see what kind of solution you have. Because a difference of 1 in the pH corresponds to a difference of 10 in the concentration, or times 10. So when a concentration, a solution, for example, has a pH of 3, and then you look at the concentration, of a solution with a pH of 2, it's a difference of pH of only 1, but the concentration of hydronium ion in the pH 2 solution is 10 times more than the concentration of the hydronium ion in the pH 3. So that's why it's nice to use the pH. And so when you know the concentration of H3O plus and you want the pH, then you use this formula that says pH equals negative log of H3O plus. If instead you have the pH and you want to know the concentration of H3O plus, then you use the second formula that says H3O plus equals anti-log of negative pH. So make sure you take the negative pH, or 10 to the negative pH. And there is this roadmap here at the bottom that shows you that. So look at the right side of the roadmap, where you have H3O plus and pH, and you have arrows between the two. So it shows you that if you have H3O plus concentration and you want to calculate the pH, you will use the formula that is on the bottom here, negative log of H3O plus. This will give you the pH. If you have the pH and you want the concentration of hydronium ion, then you would use the top formula, 10 to the negative pH. Right, so that's here to help you if you need help recognizing which formula you should use. Note here that the sig figs are particular for pH. The concentration of hydronium ion will have a given number of sig figs, and that's what you look at. But then you translate that into decimal places in the pH. So it's going to be only digits to the right of the decimal point that will matter in the pH. And they should be the same number than you have sig figs in the concentration. So that can be tricky to apply. So let's go back to the review. So what is the pH of the solution? And so here we have the concentration of H3O plus from, well, actually here, just here, right? We have H3O plus is 0.006. Let's rewrite it here. We have that. We want the pH. So when you have the concentration, we saw that we need to use the formula that says pH equals negative log of H3O plus. That's the formula you want to use. You will plug in the value of the concentration in the negative log function. So negative log of, and then you put in the 0.006 molar. Oops, molar. Okay. I've included videos on how to use the calculator, and hopefully you found those key on your calculators. But for the TI30X2S, the log function is the key just below the second function key. So just below the blue key here, if it's blue, if your calculator is blue, then LOG in capital letters is the key you want to use there. The negative sign is the key next to, between the enter and the dot. It's the negative sign in parentheses. Then you do log, the key that says log. Then you enter 0.006, close the parentheses, enter. And my calculator answer is, and let me put it in floating point, 2.2218. I'll give more because we need to 8. I'll give more because we need to decide how to run this properly. So pH has no units. So there is no units for pH, even though concentration here has a unit, the pH doesn't have a unit. So the rule for sig figs, or decimal places actually for the pH, is that you take the same number of sig figs you have in the concentration, and that will become the number of decimal places you keep in your pH. So we know we have to keep that 2 point, and then we need to decide how many decimal places. And that number of decimal places depends on the number of sig figs in the concentration. And if you look at the concentration here, how many sig figs? Can you tell me? Can you type in the chat? How many sig figs do we have in 0.006? Yes, we have only one sig fig there, right? The 6. Only the 6 is significant. So only one decimal, you need only one decimal in the pH because you have one sig fig in the concentration. So here you will only keep the first two after the point, after the dot. So that's pH. Yeah, let's show that it's pH. So this is your answer here. Let's make it this red too. So pH would be 2.2 in this case. So is this acidic or basic? You know, for those who have learned this yet, can you tell me? Acidic or basic? So tell me in this chat. So pH scale goes from 0 to 14. Yes. 0 to 14. 7.0, 7 exactly, is neutral. Below 7 is acidic. So pH below 7 is acidic. And let's just say pH above 7 is basic. So here it's acidic. And you know, it makes sense. We had acetic acid there. So pH below 7 is acidic. Okay, so now this next question is asking for the hydroxide ion concentration. So if you looked at the dissociation of water. So water, we said, is an amphoteric substance, which means it can act as an acid or a base. And that means when you put two molecules of water together, one can act as an acid, the other can act as the base. And then they can dissociate like that and you know, give the two ions OH minus and H3O plus. So when water dissociates, it gives OH minus and H3O plus. Yeah, I could write the reaction, but I'll do it afterwards. So, and there is this equilibrium constant for this reaction that says, and let's look at the reference for that. The equilibrium constant for the reaction of the dissociation of water that shows, you know, water plus water gives H3O plus OH minus. If you take the equilibrium constant, only the product will show up in the equilibrium constant, because on the reactant side, it's two molecules of water, and water is the liquid, so it would not show up in the denominator here. So that's why the equilibrium constant is called Kw. Equilibrium constant for the dissociation of water is concentration of the hydronium times concentration of the hydroxide ion equals, and so we know the value, and it's always that value because we've taken pure water and found out that those concentrations are in pure water, they were equal to 1 10 to the negative 7 for each. And when you multiply them together, it's then 1 10 to the negative 14. And this is always true. This Kw, this product of those two concentrations, is always equal to 1 times 10 to the negative 14. So that means then we can use this you know, ion product constant of water to find the formula, to find the concentration of the hydroxide ion when we have the hydronium ion concentration, or vice versa. You know, find one when you have the other. So let's take this formula and use that to find the hydroxide ion concentration. Where was I? Okay. So Kw, I guess I should directly enter that. Kw is H H2 plus times OH minus. and this is equal to the 1 times 10 to the negative 14. But here we know H3O plus, we have it here above, and we are looking for OH minus. So we need to change this formula such that OH minus, the concentration of OH minus, is by itself. So for this, you want to divide both sides of the equal sign by H3O plus. And so that means hopefully you can do this manipulation and find that OH minus is equal to, and so when you divide both sides by H3O plus, you have Kw over H3O plus. Okay, 3. O plus. Right? So that's how the formula becomes when you are looking for OH minus. It's Kw over H3O plus. And now we can plug in the values because both Kw and H2O plus are known. Kw is 1.0 times 10 to the negative 14. Negative 14. And the the H3O plus was 0.006, 0.006. And so OH minus is a concentration and it has a unit. Even though, you know, K has no unit, H2O plus has a molar unit, but then the concentration of OH minus will have a unit of molarity, you know, capital M. So let's do that in the calculator. 1.0 second, the EE key, negative 14 divided by 0.006 equals 1.6. Okay, we have to decide how many sig figs we keep here. And sig figs here are determined by, you know, mostly the hydronium ion concentration. It has only one sig fig. So, well, let me write the thing and then we'll times 10 to the negative 12. So how do we run this so that we have only one sig fig? What would be the value of the decimal part here? 2. Yes. Oops. No, that's not what I wanted to do. 1.666. The 2 will come here. And then we can rewrite that. 2 times 10 to the negative 12 molar. That's the concentration of OH minus. So that's how you would calculate the OH minus concentration. Okay.